let's start. General relativity, part 6. That came up and it said Banterian, and I was like, no, better not. So last time on our general relativity, tensors continued. And what we did was we talked about symmetric versus anti-symmetric tensors, or I should say indices inside of tensors. So for symmetric tensors, we had, you could swap the indices. We were swapping the indices mu and rho in this S, and we saw that we got the same tensor back. Oof, my rows are rough. I got rough rows today. Let's try again here. There we go. So you could, they are symmetric in the swap between the indices of mu and nu. I didn't get it, Tyrion. I did not get it. Another thing you could do is the anti-symmetric, and that means we could swap other, or we could swap indices, not S, how about A? So we have an anti-symmetric tensor where if we swapped mu and nu, we would get negative A, nu, mu, rho. There we go. So we have in this prescription a way to talk about symmetric tensors versus anti-symmetric tensors by swapping the indices. Another thing we talked about last week was the trace, and we found that we found the convenient form that we could write it as a contraction of similar indices in a single tensor. And we could talk about this as in, like, we found the trace of the metric tensor was a little bit odd. One might expect it to be 2, but we found it to be something different. We found it to be 4. So another thing we learned about was derivatives. We found out that the derivatives have a nice role in GR, mainly we talked about the exceptions to the way they transform in other spaces. So we saw that they transform under Lorentz transformations really nicely in flat spacetime, but in other spacetimes they transform differently, and we had to be careful as we moved into other spacetimes and other geometries that the derivatives and partial derivatives don't transform under Lorentz transformations nicely. They have their own types of transformations that we'll have to unpack. Another thing we did was we rewrote the Maxwell's equations. So we know the Maxwell's equations, oops, that's the wrong type of thing, as the curl of B minus the partial of T, the partial of E with respect to T, and that's equal to J. And then also we had the divergence of E, which is equal to rho. Different rho. This is just a dummy index. This is a current density. And then we had the curl of E.
No natural units?
Not yet. We'll be doing natural units soon, though. We actually have a bit of dimensional analysis to do today. So we have the curl of E plus the time derivative with respect to B, and that's equal to 0. And then we have the curl of B, which is equal to 0. And we figured out that we could rewrite these in our nice tensor notations as the following. And then we have the partial of U of this tensor, which is the stress tensor, the energy stress tensor. And then we had the bottom two equations. So this was a closed form that encompassed the top two equations, and there's a closed form for the bottom two equations, which was the partial of the same stress, or of the same stress tensor. I think I'm forgetting the name or saying it wrong. Let me look it up in a second here. Which was equal to 0. Let me make sure I'm saying that name of that tensor correctly. It is a stress energy tensor. Okay, thank you. I thought so. Okay, so that's the Maxwell's equations written down in our nice nice tensor form. So that was just an example of what you could do with the tensors after we spent 2 weeks working on them. So what should we do now? Well, we need to talk about what type of a theory general relativity actually is. So here's a hint. It's a classical field theory. Okay. Now on Wednesday we spent a lot of time talking about variational theory, like a calculus of variations, because we're doing a Lagrangian mechanics series. So that means that we are now kind of set up nicely, because GR is an example of a classical field theory so let's begin with the principle of least action. Okay, so that was one thing that we need.
Electromagnetic field strength tensor.
That's the one I meant. I don't know why. I did mean the electromagnetic field strength tensor. Okay, so we can talk about this. So let's start by talking about the principle of least action of a particle in a dimension of q. So we'll have the action is dt, is the integral of dt of the Lagrangian. Now, the so L is the Lagrangian, S is the action, and Q of t is the dimension of interest for the particle. So the particle is moving along in some dimension Q of t, and we want to find the least action. Remember on Wednesday we had, some point here, and we had some path here, and we wanted to find the least the least action.
Another way of saying Tyrions love life.
Who said that? Oh.
Your S looks like your integral sign.
Oh my goodness. It's fine. It doesn't even look like an integral sign. That is funny. Okay. Well, the Lagrangian of a point particle is typically written as the kinetic energy minus the potential energy. And if you guys are here for the first time, either from one of the raids or just you found the channel, we don't take ourselves too seriously on this channel. So we do like to learn stuff and have a lot of fun. We go through a lot of rigorous math and stuff, but we do like to joke around. Okay, so K is the kinetic, so in this situation we have K is the kinetic energy and V is the potential energy, so the Lagrangian is the difference between the two. Now, we want to minimize the action, so therefore we need to utilize the Euler-Lagrange equations. So let me write them up here because I think we're gonna want them for pretty much the rest of today. So we're gonna have the derivative of L of the Lagrangian. Welcome to the channel. With respect to Q minus the derivative with respect to time of partial of L with respect to Q dot. And this is equal to 0. Is that umbrella in the way? No, I don't think so. So for example, what if we have, so let's have a little example here. What if we have a Lagrangian that looks like the following? And this might be a Lagrangian that looks somewhat familiar. They all kind of look familiar because we see them kind of all over the place in quantum mechanics and stuff like that. But we have 1/2 times the time derivative with respect to Q, or a time derivative of Q minus the potential, which is a function of Q. And then we can find our equations by just plugging this into there. You take the derivative with respect to Q, and you get dV dQ. You take the derivative of the second, or you take the derivative of L with respect to Q dot, and then you again take the time derivative again, and you'll find out that you'll get Q double dot.
M equals 1, I assume.
Is equal to, for now, yeah. I know, I was thinking the same thing. But that was what he had in the book, so it looks, it does look like the kinetic term of 1/2 mv squared without the m. I don't think the m matters right now. You can sort of just absorb it into whatever. Later on, we're going to talk about it as kind of like a weighting factor, but for now, it doesn't really have a role to play. So maybe he just absorbs it into the Q or something like that. I don't know, but it wasn't in the book, so I'm going to follow Sean Carroll on this one. It's also, like I said, it doesn't really play a role in it, so I was okay letting it go. Okay, so here we have the second derivative with respect to time is equal to negative dv dq.
The square.
Oh, no, he has it in his book. You're right. I missed it in my notes.
So old.
I am so old. I just missed it in my notes completely. Okay, so let's keep moving along. So we got that squared away. So yeah, so it is just looking like he is missing the m, so whatever. I know my thoughts earlier were like he must just absorb that into the Q. But let's keep going here. So a field theory has a similar style to this workings. Except now we're going to replace the Q of t, so some dimension, with a field. Which you could think of like the vector space as a field on a manifold. But like we'll just say generally a field, okay? That is to say, it's some combination of coordinates inside of the R. Well, we'll talk about flat space-time for the most part. But here's an example, though, that he gives. So now we can think of the phi as a function on a space-time. So we can think of how E and M, we might think that one example of a field might look like the vector potential, right? It could be a vector potential where we have a sub 0, a sub 1, a sub 2, a sub 3, right? And all of these make up some vector potential, a mu. Now, since we're in flat space-time, this is okay. I guess he makes some remarks about how, like, it's kind of sloppy to think of the vector potential this way, but it works well for our specific example that we're working here on. So that's just an example of what this field might look like, or the functions on spacetimes might look like. So in field theory, we talk about the Lagrangian as an integral over the space of the Lagrangian density. So we might say that the Lagrangian, the kinetic minus the potential, is equal to, or the one that follows the least action at least, is equal to d3x, the integral of d3 in d3 space of this fancy L looking Lagrangian density. Oftentimes, and he makes a note of this, and my advisors made a note of this a bunch of times. Oftentimes, we usually use the words Lagrangian density and Lagrange kind of like the same way. But this is not to say, that like. We have to be careful sometimes when we're talking about Lagrange densities versus Lagrangians. But he does say that we will use that term kind of loosely as we move forward. So now the action then becomes the integral with dt times L, or of L, I should say, the integral of L dt, which is then be equal to the integral in 4 space of the Lagrange density. So now, we have a new form of action that we're going to be trying to minimize. Okay? This is a good part to where we're going to switch and talk about units for a little bit. Okay, so let's talk about units. Erase this. So now we can talk about units by saying something like C is equal to H bar is equal to K, which is equal to 1. So if we have a C is equal to H bar is equal to K is equal to 1, I did write H bar here But that's just because if you ever want to quantize the, that's right, Roosta, natural units. If you ever want to quantize this field, you could do it, but we're probably not going to get into it. I think he says in chapter 9 he talks about it, but I don't know if we'll ever get that far, so we'll see. But in natural units, we can talk about the following. I think we've shown this on stream before. It kind of eludes me. In fact, I know for a fact we've shown this on stream before. But I couldn't remember in what situation it was. But we know that the units of energy equal the units of mass. Okay, that's old Einstein's trick. And then that is equal to the units of, or the inverse of length, right? 1 over length. And that is also equal to, and we know that the units of length and time are interchangeable in natural units. So now we have it's 1 over the inverse, or 1 over time, 1 over time. So we can see that energy has this relationship with time, or 1 over time, I should say. And that makes the units of the action the following. So in the action, we're going to have, the units of the action have to be energy, units of energy, and times unit of time, right? It's dt, the integral of dt, which will give us the unit of time. So we have energy times time, so that means that this is, we'll use m as like the, how many units do you have? And that is 0, there's 0 units. This is dimensionless, okay? Which is good. But here in our last integral over in 4 space, we had the Lagrangian density. So that means that the Lagrangian density, the units of the Lagrangian density is going to be 4 units, right? Because it has to compensate for the, oh, I'm sorry. So what I should say is when we have dx to the 4th, the dx to the, in the 4 space has 1 over, is it 1 over m? Well, yeah, let's just write it like this. M minus 4, there we go. Instead of writing 1 over m to the 4th, let's shorten it. So we have units of to the minus 4th to this one, and we do want our action to be unitless, so we'll know our Lagrange density is going to need units to the 4th. So, okay, so that was kind of a side note. We'll have to revisit that a little later, I think, or at least he does. I don't know if we will or not. What are the units on that, Eric? 4. It's 4 of whatever you want. Just pick them. You can pick mass, you can pick length, you can pick time, you can pick energy, whatever. Just pick it. It'll all work out. So the
is back.
Is it back? Oh, you're right.
I require the solace of the shadows and the dark of the night.
Maybe that'd be better.
Sunshine is my
All right.
desire.
It's in my. I think it gets like the connection get loose in my pocket or something. So it. Now we have to think about the other thing. So remember the Euler-Lagrange equations preserve the action under a small variation of the fields, right? That's variational calculus. That's what we talked about all Wednesday. Means you... My phone has a crack there. I can't see it. Lose units from differentiating. It's like you have units... and think of it as 1 over length. So it's 1 over length to the 4th. Because you're when you differentiate, you lose a unit of exponents, right? So like, what's a good example? Velocity is meters per second, or let's be a little bit more unit nice. Length over time. Acceleration is length over time squared, right? So what's the change from velocity to acceleration? Well, velocity, the derivative with respect to time of velocity is equal to acceleration. So what are we doing? We're taking the derivative of this, and we're basically subtracting one of these units of t away. So if you had t to the 1 here, which is what it is, then you take the derivative and you're lowering that exponent to 2, because you're going from t to minus 1 to t minus 2. Does that make sense? So where are we at? Oh yeah, so we can say that we want, so the calculus of variations is trying to figure out how things are going to change, small variations of the fields. So let's take a look at this. So let's make a small variation to the field. So we'll add some tiny variation to the field. And then if we were to take the derivative, then we'll end up getting the derivative of the field plus a variation of the derivative of the field, and then we're going to send that variation through. So this is going to be plus the derivative of the variation of the field. There we go. Nope, I missed the variation. There we go. Okay, so now we send that through, and now we have what it looks like when we have our new fields. Okay. Now, since this is very small, okay, we can Taylor expand under this variation. So you guys remember your Taylor expansions. Let's take a look at the Lagrange density. So our Lagrangian is going to, our Lagrangian density, Lagrangian density, are going to go to the following. I should have made this lower. Oops. Miss. Oops. Not equal. Of, where is it? du of the variation. There we go. Okay, so that's the Lagrange density, and then we can simplify this to the following. And this is where it starts to get... so when we make the variation, when we Taylor expand it, we'll have to do the whole derivative, the function, I'm going to take the derivative, and then do this. We're only going to do it to one. To one order, though, leading order. Or not leading order, but I guess if you count, I don't know what you guys count, the first order and the second order, so. I count this as not counting as an order. Oh wait, hold on, that's not right. I mean, the original Lagrangian density, and then we have our next approximation. The first order of approximation is the derivative of the Lagrangian with respect to the field times the variation, plus this monster of a derivative here. Derivative of the field. This thing's a little bit messy, but we actually have a tool to figure it out. Variation. Oh man, this thing's long. There we go. I fit it all though. We actually have a tool to help us understand this one, but this thing's kind of a bit of a pain. Your internet's poo-poo. I'm sorry. Well, good to see you, though. Thank you for coming. It's always good to see you. So this is our Taylor expansion in the field. We now have recovered the original Lagrangian density plus the two variations. And this is a first order approximation. Now, this shows us that we have an S. Our S can be taken to S plus some small variation of S. And I think this is what you all have been waiting for. We wanted to see that small variation of S. And we can look at that. Okay, so now we want to find that small variation of S. I think I can open this door back up if you guys are okay with it. Give me just a second. It might be loud. But it is a gorgeous evening tonight, so I want to take advantage of that while we still have them. because we won't have them for long. So the goal is going to be to figure out what this is just going to be the action as it is. And we want to make sure the whole calculus of variations thing was to figure out how the functions under the integral are going to change under small variations. So we're going to try to, we know what this is. We know we need to find the least one of that using Euler-Lagrange. Let's try to figure out what's going on with this thing, okay? Let's get rid of all this. The board, it's going to be a little bit board intensive now, so. Or equation intensive, I should say. Well, we can erase that. You guys know that the action plus the action, or the action's going to the action plus the variation. So what is that variation? That's the integral in 4 space of, and let me rewrite what I had down there. So it was, and this is, so this is our Taylor expansion. This is the monster right here, this huge derivative that I was warning about. Even Carroll warns about this derivative and says it's very tricky to go through, but there's kind of a cheat we're gonna do that we did on Wednesday as well. And that is, remember how we did that rearrangement of path integration? Yeah, it's soon. It's nighttime by 4:30. That's true. I'm gonna be like an hour into stream. It's gonna be dark, pitch black. That'll be funny. That'll be interesting. It won't really be pitch black, but it will be before we end stream. So now we have a nice evening night. Let's enjoy it. But the trick that we used on Wednesday, and we're gonna reuse it again. We have to tackle this thing by using integration by parts. So let's just look at this thing. And if you are unfamiliar with this, hop over to my YouTube channel, the Lagrange Mechanics first episode. We do this. I don't know where it is, but I think it's towards like about 2/3 of the way through. Or you can just watch the whole thing if you'd like. But it's kind of long, so as most of my series lectures are, or discussion series things are, whatever. But here's what this part looks like, okay? And that's going to be the integral in 4 space of this Lagrangian. The derivative of the Lagrangian with respect to the derivative of the field times the derivative of the variation of the field. And in this integration by parts, we're going to get the negative derivative for x. You can just take my words for it. I'm mostly taking Sean Carroll's words for it. Maybe one day we can actually sit down and work this out, but I think this one's going to be a brute of a integration by parts to work out, but it definitely is doable. And it's just going to be about picking the correct forms for u and v. Variation of the field. Can I fit this all in one line? I'm going for it. I'm going to go for it. The integral in 4 space of the derivative of the Lagrangian with respect to the derivative of the field times the variation of the field. And the goal is to isolate the variation. Good. The goal is to isolate the variation, right? That's what we want to do. We want to get the variation on the outside of the integral, so that way we can factor out of this. Because right now we can't factor it out because there's no lonely variation in here. This variation is being applied on the derivative. Which is why we want to make sure that we can pull it out. But in this side of the equation, we have 2 things that both have this one has a derivative with a variation inside, but this one does not. Luckily for us, this integral right here is the same thing we did on Wednesday, except it's really messy, but it's really the same thing. It is, remember on Wednesday when I said eta of n1 is equal to eta of x2, which is equal to 0? Why was it 0? Well, because the eta was the change in the function, and the change in the function didn't exist at the endpoints. right? So at the endpoints, there was no change. We're applying pretty much the same concept to here. However, so for that one, we're basically saying that this is a boundary condition and that the boundary condition has to be 0. Okay? Now, there are situations that Sean Carroll warns us about maybe later on we might have to deal with. One of those is the instanton. I think he says, yeah, instanton calculations in Yang-Mills theory. That's not the case, and we actually have this extra field, and it's very messy, and there's other ways, other tricks to solving it. But for everything that we're worried about in this discussion series, this is a boundary condition. We're going to send it to 0 because that's what happens at the boundary. The same way that we talked about the variations of eta on Wednesday, okay? So this is what we want. This now takes the place of this, and we can rewrite our variation on the action as the integral of d4x. I should probably stick with my notes, although I've already failed to read them once tonight, but we're going to do it anyways. Of the derivative of the Lagrangian with respect to the field minus the derivative of the derivative of the Lagrangian with respect to the derivative of the field. Close that, and now we have factored out the variation. Now, if you remember, we talked about variational derivatives. The variational derivatives, we talked about it in path integration, actually, because that's where functional derivatives, excuse me, thank you for correcting me. Functional derivatives, thank you. Functional derivatives is the word I meant. It even says so in my notes again. We're reading the notes. And we know that the functional derivative, thank you. So we know that it has to satisfy this formula right here. It's the same thing that hit us with the Euler-Lagrange equations, right? We had this exact form in the Euler-Lagrange equations. Just like our alpha, we wanted to figure out what happens, the alpha from Wednesday, that is. We wanted to figure out how to make this least action a 0, and by doing it, we can set this equal to. So we'll take our functional derivative. To minimize it, we need to set it equal to 0, but it also gets set equal to the Euler-Lagrange equations. The derivative of the Lagrangian with respect to the field minus the partial of the derivative, partial of the Lagrangian with respect to the to the derivative of the field. Woof. And this was our Lagrange equation that was equal to 0. Right? Or our Euler-Lagrange equations that were equal to 0.
Come here, Darla. The people need you.
Now again, remember we had a couple stipulations about this, right? Like this was so far we've been very reliant on the fact that this is flat space-time, right? That was one of the things about the Lorentz invariant derivatives and everything that we've talked about in that regard. So we want to make sure that we're very clear about where this works right for now, because it could change under a different metric, right? So now let's do one example, okay? We're going to do an example of all of this that we've learned. There was 2 examples in Sean Carroll. One of them is simple, and one of them is very difficult. I will not be doing the very difficult one. After this, we're going to go right to manifolds. So if you all are following along with Sean Carroll, I'm not going to talk about E and M and the complex field of a complex field. So we'll talk about a scalar real field. Okay, a single real field, I should say. We'll leave that last line because it will be helpful. So in the classical mechanics of a single real field, we'll have a kinetic energy equal to 1/2 times the field, the time derivative of the field squared. Make sure we get that squared. Then we'll have what's called the gradient energy. Which was 1/2, oops, times the derivative of the field. And then the potential energy. I'm always so used to it. We're going to be doing the del inversion soon. So like every time I see a symbol, I think it's some like, you know, weird, crazy thing still. It still happens. I still see symbols and think that's weird and crazy, and it turns out to be fine. So then we have the potential energy. I should do arrows, not equals. Okay, so then we could have, so the Lagrangian could just be the combination of all of those things. However, the kinetic energy and the gradient energy are not by themselves Lorentz invariant. Check out the brains on Brad. That's funny. But we can combine them into something new, or something not new, it's just something different, right? And that is, we can write them with tensors, tensorally. Is that the right word? Tensorally? We can write them with tensors. So have the tensor like this. Using the metric, which has the -1 plus, or negative plus plus plus, right? And applied to this, and this is equal to our kinetic energy minus our gradient energy, which makes sense, right? The gradient is basically the derivative with respect to the different directions, x, y, and z. And then this one is respect to time. So if we multiply it by our metric, we're basically just working our way down the metric with 0, 0. Notice how these contract, so you want to sum over like terms. So you get 0, 0, 1, 1, 2, 2, and 3, 3, all within that field, or all within that stuff. And now we know it's Lorentz invariant, right? Because we're applying it to the metric. Gradients are certainly pretty weird, crazy things. It totally depends on the context of it, but it definitely can get really weird really quick. So for this Lagrangian, if we want to find the Euler-Lagrange equations, we really need to figure out what these two things are. So let's figure them out really quickly. So for this particular example, we'll have the derivative, the partial of the Lagrangian with respect to the field is equal to the negative derivative of the potential with respect to the field. So that looks good. The next one is the partial of the Lagrangian with respect to the derivative of the scalar. And that's going to equal the negative metric times the derivative of the scalar. Okay? Now this particular derivative is actually kind of a bit of a beast to get. If anybody would like to know, I can post a picture of that to Discord, but we're not going to go over it because it takes a lot of time. I did not write it in the notes either because it took a decent amount of time. It is relatively straightforward, but you do have to do a little bit of tensor crunching. Nothing too nutty. But you get some Kronecker deltas you'll have to get worked out and stuff like that. So, but I can take a picture and put it in Discord. So just let me know if you guys would like to see this derivative worked out with tensor notation. Now, substituting this into our Lagrange equation, right? We want this. We'll get the D'Alembert. Did I say that right? D'Alembert. I say it. D'Alembert. dv d phi is equal to 0. The D'Alembert is in tensor notation, because we'll talk about it in tensor notation. It's the gradient, or I'm sorry, not the gradient. It's the metric. Welcome to the channel. Things get a little bit weird. Applied to the partial of u and v. McGaggy, welcome to the channel. Thank you for the follow. Did I say your name right? McGaggy? Majaggy? I'm sorry if I pronounced that wrong. Welcome to the channel. It's good to have you. I'm sorry I'm pronouncing your name terrible. Anyways, it's so in flat space-times, this is flat space-time. This is the equivalent to the double derivative with respect to time, basically the acceleration. The second derivative, or the second gradient, I don't know what you call that, the second derivative in the spatial components of the second derivative, we'll say it like that, plus dv d phi is equal to 0. A popular choice for the potential is that of the simple harmonic oscillator, right? So that pendulum motion, someone said pendulum motion early on. All good, excellent. Well, it's good to see you. What was I saying? Yeah, so a popular choice of that is simple harmonic oscillator motion, right? So we have V, the potential, is going to equal 1/2 m, there's the mass, m squared, field squared. I think I dropped that squared in my notes. That one I'm pretty sure is supposed to be there. Yeah, it's supposed to be there for sure. Okay, so now, if you are following along the notes, you want that simple harmonic oscillator to have that m squared. So now, therefore, we're almost done. The equations of motion. Am I above chat? I am above chat. The equations of motion for a simple harmonic oscillator in a classical field theory is as follows. The D'Alembert applied to the field. I think something's wrong here. Wow, really? Okay. Nope, that's the way it is. Oh, because it's, I see, second derivative. We good. Minus m squared phi is equal to 0. So that's what we've done. We've done that. We found the simple harmonic. With the simple harmonic oscillator, we can plug it in to the potential for our Euler-Lagrange equations. We can get the equations of motion. And do you know what it means? You know what it means? You know what that is? 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 That's our good old friend. Gotta love him. The Klein-Gordon equation. Again, how many times have we seen the Klein-Gordon equation on this stream?